You know what bothers me? And I mean this genuinely. It's bothered me for 50 years. What bothers me is that we teach gravity wrong. Not a little wrong, fundamentally wrong. And we do it confidently, in every classroom, to every kid. And then we wonder why people find physics confusing later on. We tell them gravity is a force. It isn't. Now look, I'm not saying Newton was an idiot. Newton was probably the greatest scientific mind who ever lived, and I don't say that lightly. But Newton himself knew something was off. He wrote about it. He said he couldn't understand how a body could act on another body across empty space with nothing in between. He called it an absurdity. The man invented the equation and then said the equation was absurd. So when I tell you gravity is not a force, I'm not being provocative. I'm not trying to be clever. I'm trying to tell you something that Einstein figured out in 1915 and that most people, including most people with physics degrees, don't really have in their gut yet. So pull up a chair. We're going to do this properly. I grew up in the South Bronx. My father was a plumber. We didn't have books about physics in the house. I got into this almost by accident. I was working construction, actually, and someone suggested I try taking a physics course, and something just clicked. And one of the first things that clicked, one of the first things that felt real to me, was the question of what things actually are versus what they look like from far away. Newton's gravity looks like a force. From far away, from the outside, it behaves like one. You can write an equation for it that has force in it, and that equation will give you correct answers for an enormous range of problems. But that doesn't mean it is a force. Here's an analogy I like. Suppose you're watching a movie on a screen. The picture looks three-dimensional. The actors look like they're moving in space. But if you walk up and touch the screen, it's flat, two-dimensional. The three-dimensionality was an appearance. A very convincing appearance, but not the underlying reality. Newton's gravity is the appearance. Einstein's geometry is the screen. Let me tell you about the thought experiment that cracked this open. Einstein, and this is him talking, not me. Einstein said the happiest thought of his life was this: a man falling from a roof does not feel his own weight. That's it. That was the thought. A man falling from a roof does not feel his own weight. Now, why is that the happiest thought of his life? Sounds kind of morbid, doesn't it? But think about what it means. When you're standing on the ground, you feel weight. The floor pushes up on you. You feel that pressure in your feet, your legs, your back. That's real. That's a physical sensation. Now imagine you step off a building. God forbid, but imagine it. For the time you're falling, before anything else happens, you feel nothing. Zero. You're weightless. Your stomach goes up. If you had something in your hand and you let go, it wouldn't fall relative to you. It would just float there beside you. Because you're both falling at the same rate. That weightlessness, that nothing, is what Einstein called the local inertial frame. It's what you feel when gravity is the only thing acting on you. No contact forces, no floor pushing, nothing. And here's the key point. That nothingness, that weightlessness, is identical to what you'd feel floating in deep space. Billions of miles from any planet or star, no gravity anywhere near you. You'd feel exactly the same nothing. So what does that tell you? It tells you that free fall and zero gravity are the same thing. They feel the same. They are the same. And if they're the same, then maybe, what we call gravity isn't a force acting on you at all. Maybe it's the absence of force. Maybe free fall is the natural state, and standing on the ground is what's weird. I want you to really sit with that. The force, the real force, is the floor. The floor is pushing up on you right now. The electromagnetic force of the atoms in the floor fighting against the atoms in your feet. That's a genuine force. That's something real acting on you. Gravity is not doing that. Gravity is just the shape of the space around you, and what it wants to do is let you fall. The floor is the thing stopping it. Alright, so if gravity's not a force, what is it? It's geometry. I know that sounds like I'm replacing one abstract word with another abstract word, so let me be more careful. Einstein's insight. And this took him 8 years to work out fully, 8 years of some of the most intense mathematical work anyone has ever done. His insight was that space and time are not separate things. They're one thing, spacetime. And that thing has physical properties. It can be curved, it can be warped, and mass, matter, energy, anything with mass, curves the spacetime around it. And when spacetime is curved, objects moving through it follow the curves. Not because something is pulling them, but because the geometry itself is different. The shape of space is different near a massive object than it is in empty space, and objects follow the shape. Now I know the standard analogy here is the rubber sheet. You put a bowling ball on a rubber sheet, it dips. You roll a marble, it curves. I use that analogy too, but I want to be honest with you about what's wrong with it. The rubber sheet is two-dimensional. The real thing is four-dimensional. And in the rubber sheet, the marble curves because of gravity. Gravity from the earth beneath the sheet, pulling the marble down into the dip. So you're using gravity to explain gravity. That's circular. The actual picture is four-dimensional space-time that curves not because of any external force, but because of the intrinsic geometry. Because mass changes the metric, the mathematical description of how distances and times are measured of the space around it. And then objects don't follow straight lines anymore. They follow what we call geodesics, the straightest possible path through curved space-time, which, when you project it back into 3 dimensions, looks like a curve, looks like a falling apple or an orbiting planet. The apple isn't being pulled down. It's following the straightest path available to it through curved space-time, and that path goes toward the Earth. That's gravity. Now here's where I see people get confused, even people who think they understand this. They hear curved space-time, and they think, okay, so space is bent. The apple follows the bent space. Got it. But they're only getting half of it, the space part. And actually, and this is something I want to emphasize, for ordinary gravity, for the kind you experience every day, the time part is more important than the space part. Let me say that again. The curvature of time is more responsible for the gravity you feel than the curvature of space. What does that mean? It means that time runs at a slightly different rate depending on how close you are to a massive object. Time runs slower at the surface of the Earth than it does at the top of a mountain. Not a lot. Tiny amounts. But measurable. We've measured it very precisely. And that gradient in the rate of time, the fact that time runs slower here than it does up there, is what creates the effect we call gravitational pull. Objects moving through space-time naturally move toward regions where time runs slower, toward the Earth, toward the floor. The apple falls not because space is curved under it, but because time flows differently on the side of the apple closer to the Earth than on the side further away. The apple follows that differential. It moves towards slower time. I know that sounds strange. It is strange, but it's what the math says, and the math has been verified over and over again. Your GPS, the thing on your phone that tells you where to turn, works because engineers accounted for exactly this. The satellites are high up, where time runs slightly faster. The GPS signal has to correct for that difference, or you'd be navigating to the wrong location within minutes. General Relativity is in the code running on the satellites above your head right now. This is not abstract. This is engineering. I should be honest with you about where the frontier is. General Relativity is, as far as we can test, right? We've tested it extremely precisely. Gravitational waves, the bending of light, the precession of Mercury's orbit, GPS, black hole shadows. It keeps passing every test. But it's not the final word, because we also have quantum mechanics. And quantum mechanics is also, as far as we can test, right? It describes atoms, electrons, photons, the structure of matter, with precision that is almost unbelievable, better than 1 part in a billion in some cases. And the two theories don't agree. When you try to apply both of them at the same time, when you try to describe gravity at quantum scales or quantum effects in extreme gravitational fields, you get nonsense. Infinities. Contradictions. The math breaks down. We don't have a theory of quantum gravity. We don't know, at the deepest level, what gravity is. We know what it looks like. We know how to calculate with it. We have Einstein's beautiful geometric picture. But the quantum nature of gravity, how space-time behaves at the Planck scale, what happens at the center of a black hole, we don't know. That's what I've been working on for most of my career. The connection between gravity and quantum mechanics. There's something called the holographic principle, the idea that the information describing what happens in a volume of space is encoded on the boundary of that space, like a hologram. It's strange. It might be important. We're still trying to understand it. I'm in my 80s. I'm still working on it. I'm not done. And I tell you that not to be dramatic about it. I tell you that because I want you to understand that the question, what is gravity, is not a question that has been answered. We've made enormous progress. Einstein made the biggest single leap. But the answer is not in hand yet. That's the honest truth. Let me talk for a minute about why this is hard to communicate. Because I've been teaching for a long time and I think about this a lot. The problem is that our intuitions are Newtonian. All of them. Every single one. You were born into a world of medium-sized objects moving at medium speeds under what feels like constant gravity. Everything you learn to do, walk, throw, catch, drive, is calibrated to Newtonian physics. Your brain has spent your entire life building and refining a model of how the world works. And that model has gravity as a force in it, baked in at a very deep level. And then I come along and say, no, actually, it's geometry. And you say, okay, sure, geometry. And you nod, and you think you've got it, but you haven't got it. Not in your gut. Not in the way that you'd need to really use it. Because your Newtonian intuition is still there, still running in the background, still the thing your brain reaches for when it needs to quickly understand a situation. The only way to really build a new intuition is to spend a long time with the mathematics. Not because the math is the point, the physics is the point, but because the math forces you to be precise in a way that language doesn't. When you work through the tensor equations of general relativity, when you calculate how a geodesic behaves in curved spacetime, you start to develop a feel for it. Not a visual feel. You can't visualize four-dimensional curved spacetime, and neither can I. But a mathematical feel, a sense of how the geometry behaves. That takes time. That takes work. There's no shortcut. What I can do, what I try to do in my lectures, is give you the right concepts to hold on to, the right questions to ask, the right things to be confused about. Because being confused about the right things is actually progress. Being confused about why a force can act at a distance, that's Newton's confusion, and it's a good confusion, and it leads somewhere. You're in a sealed box. No windows. Could be an elevator, could be a spaceship, could be a closet. Doesn't matter. Scenario 1. You're sitting still on the surface of the Earth. You feel your weight. You stand on a scale. It reads your mass times g, whatever that is for you. Scenario 2. The box is in deep space, far from everything, but it's accelerating. Rockets are pushing it upward at exactly 9.8 meters per second squared. You feel weight. You stand on the scale. It reads the same as before. Question: can you tell the difference? From inside the box, with no information from outside, can you tell whether you're on Earth or accelerating in space? Einstein said no. You cannot. The two situations are physically equivalent. This is the equivalence principle. Gravitational mass and inertial mass are the same thing. Gravity and acceleration are the same thing. Locally, meaning in a small enough region of space, you cannot distinguish between them. Now flip it. Scenario 3. You're in the box and it's in free fall. Elevator cable snapped. You feel nothing. Weightless. Scenario 4. You're in the box and it's in deep space. Not accelerating, just floating. You feel nothing. Weightless. Again, can you tell the difference? No. Locally, you cannot. Free fall and floating in space are the same. Sitting on the ground and accelerating upward in space are the same. What does this tell you? It tells you that gravitational force and inertial force are the same thing. And if they're the same thing, then maybe they're not two different things at all. Maybe there's just one thing, the geometry of space-time, and what we call gravity and what we call inertia are both expressions of that geometry. That's Einstein's leap. That's what took him 8 years to make mathematically precise. But the conceptual heart of it is in that elevator. It's in that moment of equivalence. If you remember one thing from this conversation, let it be this. When you feel weight, when you feel the floor under your feet, the chair under you, the ground, that feeling is real. That's a real force. That's the electromagnetic force of matter pushing against matter. That's contact. Gravity is not that. Gravity is what you would feel if the floor disappeared. Gravity is what you feel in free fall. It's nothing. It's the absence of contact. It's the universe letting you follow the shape of space-time without anything getting in the way. The Earth is not pulling you. The Earth's mass is curving the space-time around it, and the natural path through that curved space-time goes toward the Earth's center. The floor is in the way. The floor is what you feel. The floor is the force. Gravity is the geometry. I know that's strange. It should be strange. If it doesn't feel a little bit strange, you haven't really heard it yet. The universe is stranger than Newton thought. It's stranger than most people think. And the job of physics, my job, the job I've been doing for 50 years, is to keep asking how strange, and to keep finding that the answer is stranger than we expected. I started doing physics because something clicked. Something felt real in a way that other things didn't. And that thing was, the universe has actual answers. Not approximate answers. Not useful answers. Actual answers. About what things are, how they work, why the numbers come out the way they do. You may not be able to see them directly. You may need mathematics to find them. You may have to spend years building the right intuitions. But they're there. The universe is knowable. Imperfectly, slowly, with a lot of wrong turns. But knowable. Gravity not being a force is one of those answers. It took us until 1915 to get there. It might take us another 100 years to understand what gravity is at the quantum level. But we're moving toward it. And I genuinely think, that the people watching a video like this, the people who are curious enough to sit with a hard idea for 20 minutes instead of moving on, those are the people who are going to help us get there. So, thank you for sitting with it. Go look at the lectures. Do the work. Be confused about the right things. That's all any of us can do.